All right, so a quick recap of what we talked about yesterday. We introduced some of the terms in electrochemistry concerning reduction and oxidation. Uh, we learned the importance of oxidation numbers as far as determining whether a reaction was in fact a redox reaction or not. And we learned how to balance somewhat complex redox reactions using the half reaction method. And that's pretty much where we left off last time, balancing the one reaction from your oxalate lab involving permanganate in acid and both basic conditions. So are there any questions or comments on any of the stuff that we talked about yesterday? All righty. Okay, so now what I want to do is just take a quick look at batteries because this is the topic of the experiment that you guys are doing now. And so, uh, first of all, we introduced the two general categories of redox reactions, and one was direct redox reaction, where the two reactants, the thing that is being oxidized and the thing that's being reduced, are in physical contact. And examples of that are rust um, and patina on copper and stuff like that, and statues. um, Now we get to the indirect redox reaction, and that's where we physically separate those reactants in space and bridge them with a wire, essentially. And also, there's got to be a salt bridge in there to maintain electrical neutrality. And we'll talk about what that means specifically in a little bit. But anyway, I have a setup here for what's called the Danielle cell on this PowerPoint slide. And so we have the zinc half cell to the left and the copper half cell to the right. And so you're going to get to build this in lab and find out its voltage potential. But anyway, this is the general setup. So the electrolyte solution that the zinc is in under standard conditions is this 1 molar zinc 2 plus. And this can be created by putting in some sort of a soluble salt. In lab, I believe you are going to use zinc sulfate. And so that breaks up into zinc ions, and then you get a spectator, which we don't often show here. So that's 1 molar. And then in that 1 molar solution, you have an electrode that's made up of zinc. And the definition of an electrode is any solid surface that allows for an exchange of electrons. So that exchange can be either a gaining or a losing of electrons. And when it's a losing of electrons, we call that electrode an anode. And you could remember that because losing electrons is oxidation, and that begins with a vowel, and anode begins with a vowel, the O and the A. When the electrode supplies a solid surface where electrons are gained, then that electrode is called the cathode. And you could remember that cathode because it begins with a consonant, and so does reduction, and that is the definition of the gaining of electrons. All right, so this Danielle cell the copper zinc cell is made up of a zinc half cell and the copper half cell. Over here we have a copper electrode, and that's dipped into 1 molar copper 2 plus solution. And I believe that's the source of that in your experiment is copper sulfate. But anyway, this is pretty much the setup. You see the voltmeter reading here is 0 at this time. So what we can do is we can weigh these electrodes before we close the switch. Now, once this switch here is closed, we connect the wire and everything's set up. The voltmeter reading goes to 1.10 volts. All right. And we can let that discharge for a little while, and then we can stop it. And we can take out this zinc electrode and weigh it. And we find when we weigh this, the zinc electrode loses mass. And the zinc solution here increases in concentration. On the other hand, on the other side, we find that the copper electrode increases in mass. And we find that the solution, after a while, loses concentration or decreases in the copper concentration. All righty, so now I set up everything that happens for you. Can anybody explain the half reactions that are involved in this cell that would explain the experimental evidence of gaining and losing mass on the electrodes and increasing, decreasing concentration? For example, why do you think that the zinc gains mass? I'm sorry, it loses mass.
Does it have something to do with the zinc being the anode?
Yes, it does. It does. So zinc being the anode, that means it's obviously it's getting oxidized. And so that gives up electrons. So the half reaction that must be taking place right on that zinc electrode is one where, here, let me just rip my computer apart a little bit, is one where the zinc must give up 2 electrons and then dissolve into solution as zinc 2 plus ions. And that would explain the increase in the concentration of zinc, and it would also explain the loss in mass of that electrode. All right, so what's happening over here on the copper side?
It's gaining copper.
Yeah, so how we can explain the decrease in concentration because this side, the reaction that's taking place over here is the copper 2 plus ion in the solution is coming up to the copper electrode. It grabs 2 electrons and plates out as copper solid. So we see that when we have this setup, this indirect redox taking place, electrons, once we attach the wire, electrons are going to flow through the wire in this direction, towards the copper, build up on this copper plate where the copper ion can come up from the solution, gain the electrons, and plate out over the existing copper, and therefore explain why the electrode copper gains mass. And like we said, the zinc loses mass. Now, once we put that wire in there, we don't have to put a voltmeter in there. We could put a light bulb, or we could put a little motor or something like that and tap into this free energy. So for this process, which we call a voltaic or a galvanic cell, for this setup where electrons spontaneously flow from the zinc half cell to the copper half cell, what would the delta G for this setup be? Would it be positive or negative?
It's negative.
Yeah, and it's negative. You know it's negative because,
It's spontaneous.
yeah, because it happens, you just connect it and the electrons flow, and you don't have to do anything about it. Now you can tap into this natural flow of electrons to run things, and that's why delta G is sometimes equated to the maximum possible work that you can extract out of any natural process. And that's why it's called the free energy. Okay. All right. Any questions on that? So I think that's a pretty good introduction to batteries and how they work. So you have something that's preferentially reduced, connected to in some way with a wire, something that's preferentially oxidized compared to each other. Now, that doesn't mean that this thing is always going to be oxidized and the other thing's always going to be reduced. In order to do that, we have to get some sort of a relative propensity for the attraction of electrons. Okay. Anyway, this next plate goes into stuff that we already talked about, so I'll skip over that. This details some of the findings that we made, including guessing the sign of delta G. And so we went all over that. You can look at this. This plate here says, well, it kind of should make sense if you look at it from a perspective of water naturally flows from higher ground to lower ground. You can think of electrons flowing from higher potential to lower potential or something like that. And so we have all of these analogies. We call this the gravitational force. Sometimes this is referred to the electromotive force. We can tap into this natural flow of water from higher to lower ground and make energy from it, just like we can make batteries. Now, if we need to pump water out of our basement, even though that's a non-spontaneous reaction, we can do that by putting in a power supply of energy strength that is greater than what we could have extracted from the natural process. For batteries, we could make what's called an electrolytic cell, which could run non-spontaneous redox reactions. In other words, run those spontaneous redox reactions in reverse by hooking them up to a power source, another battery maybe, that has a higher voltage potential. And then this last thing I just slipped in there because this is what we're going to talk about next, when we want to measure the heights of mountains and things like that, we pick a standard, and that standard is often sea level. But we didn't have to pick sea level as a standard. We could have picked the center of the earth or some other reference point. But it doesn't matter if you pick the same standard. Then I know that this mountain is so high, 9,000 feet compared to sea level. I know this other mountain is 8,000. So I know that the difference between the two mountains is 1,000 feet in elevation. And it's the same thing with electrochemistry and these voltaic cells. We need to pick a standard. We don't have to measure the absolute potential of any one of these half cells for being reduced or oxidized. All we need to do is measure it relative to the same half cell, and then we can tabulate those values. And then from those values, we can tell the difference between the potential of any two half cells. And that's our voltmeter reading. That's a potential difference. So the half cell that is picked for electrochemistry is called the SHE. It's the standard hydrogen electrode. And so research groups around the world have built these standard hydrogen electrodes, and they connect these to all the other half cells and find the relative voltage potential between the two. All right, so here's the setup for the standard hydrogen electrode. We have some tank of compressed gas with a valve that's built to make sure that there's 1 atmosphere maintained, because we want to do all of these experiments under the same conditions. So when we measure all these half cells up against the standard, it's under standard conditions, and that's what the superscript 0 on this E reduction value signifies. So if there's any gases involved, they have to be 1 atmosphere. If there's any solutions involved for the electrolyte, then they have to be 1 molar. And the whole setup has to be at, as you probably can guess, 25 degrees Celsius or 298 Kelvin. Okay, so that's pretty much the setup. Now notice that this standard hydrogen electrode is written as a reduction. So in the solution, I have my 2 H plus atoms gaining 2 electrons, and then bubbling off here as H2 gas. Okay, and then if the pressure goes above 1 atmosphere, this valve lets gas out. But anyway, it's written as a reduction, and we define this cell potential as being 0. So that's our starting point. Now, the other half cell, you can imagine maybe it's over here somewhere in a beaker, and it has an electrode in it. Now, this guy has a platinum electrode for the standard hydrogen setup for that half cell. And the reason why we have to put in this platinum electrode is because if you look at this half reaction, there are no solid surfaces involved in this half reaction. So we have to supply a solid surface. Now, in the previous example, we had copper and zinc, and we have solids under standard conditions of copper and zinc that can provide a surface for the exchange of electrons. So For the copper and the zinc, we have solids, and those electrodes are called active electrodes. They're called active electrodes because they're involved in the redox reaction. If we go back and we look at the redox reaction, then you'll see that for the zinc, we have solid here, and for the copper, we have solid there. So we have solids in those ones, but like we mentioned before, there isn't a solid for the standard hydrogen electrodes, so we have to apply this platinum electrode. And this platinum electrode is what they call an inactive electrode. All right. Let's see, what else can I tell you about this? Now, in lab, when you do this, there's going to be one half cell that you're going to use that needs an inactive electrode, but you're not going to use platinum. You're going to use graphite. So sometimes we use graphite. And it turns out that graphite works almost as well. And it costs a fraction of the price of platinum. So it's a lot cheaper for us. And so we use that, and it works almost as good as platinum. Now that one half cell that you guys are going to be using in lab that needs this graphite electrode is the iron half cell, because in this half cell that you're going to have in lab, so it's in a beaker and there's a solution, and you're going to have your platinum, not platinum, the graphite rod in there. In this solution here, you're going to have iron 3 plus and iron 2 plus. So you're not going to have any solid iron in this half cell. And there's reasons, good reasons not to have solid iron dipped in some aqueous solution, is because it's going to rust, and that's going to just wreck everything. So the redox reaction that can take place in this half cell is the iron 3 plus getting reduced with one electron to go to the iron 2 plus. And so for this half cell reaction, there's no solid. These are both ions dissolved in water. All right, any questions so far? All right, we're good. Okay, so let's see how an experiment might work to determine the half cell potential based off of a standard hydrogen electrode. And you guys, you can look this up probably on YouTube and see some videos, which are kind of nice because either they show you what would it look like in lab, or they show you some sort of a diagram and a cartoon kind of thing of what they believe is going on at the atomic level as far as the electrons and the atoms. And so that's kind of nice to see a picture just to help you in your mind visualize what's believed to take place. But anyway, here we have a setup, and the standard hydrogen electrode is on the left, and then we have some other electrode on the right. Now, when the electrode on the right is the copper, we have a copper metal here and 1 molar copper 2 plus solution, we find that, and hook it up, we find that the electrons flow from the standard to the copper, and that takes place spontaneously. Furthermore, the voltmeter reading, this is the I guess voltmeter, which is what we call for this case E reduction 0, or sometimes E cell. This is E cell. That's the overall cell potential under these standard conditions. All right. Now, when we replace the metal over here with zinc, then the electrons flow the opposite way. They flow from the zinc spontaneously to the standard hydrogen electrode, and we can define the oxidation potential for zinc. Now, because of the relationship between the oxidation potential and the reduction potential and the negative sign, we know that the reduction potential is going to be opposite that. And we'll talk a little bit more about that in a second. But anyway, we're comparing to the standard. So if I looked at what we talked about sea level before, and instead of voltage or potential difference, we said like meters maybe, you might use an analogy something like this, and that is that copper is ranked above the standard by 0.34 meters, and therefore is preferentially reduced by the standard, as opposed to the zinc half cell, which is ranked below sea level compared to the standard, and therefore the electrons go from the zinc to the hydrogen electrode. So that's one way. It's kind of not a great analogy, but it's an analogy. So you can extract for what you think it's worth. All right, here's a recap. Oh, we didn't mention the salt bridge, and this brings into what the salt bridge does. So if we have a salt bridge here in this setup, let's go back here. Okay. Now the salt bridge helps maintain electrical neutrality. So what does that mean? That means that there must be an electrical buildup that has to be neutralized. And we see that the electrons are flowing from the zinc to the copper half cell. So this cell over here is gaining negative charge. So it's going to have a negative charge buildup. And you know, like charges repel. And so electrons are going to repel and they're going to stop flowing pretty quickly. So in order to neutralize this negative charge buildup, we connect the salt bridge. And in lab, your salt bridge is going to be made up of potassium nitrate. So you have a salt solution in there. And so I have a negative charge buildup over here on this side because electrons are flowing. So can anybody guess what'll come out to neutralize negative charge from the salt bridge?
Potassium.
Yeah, you got it. And so on the other side, we have a positive charge buildup because it's losing negative. And so out here, you probably could guess, is going to be the nitrate or the negative charge. So that's how salt bridges work, to maintain neutrality and keep those electrons flowing through the wire. think that's, while I'm here, let's talk a little bit about a few of the other definitions. Now, since electrons are flowing to the copper electrode and electrons are negatively charged, it would make sense that this electrode over here give the convention sign of positive, right? Because electrons go towards positive things. So we're going to define that electrode to be positive. It's also the electrode where reduction is going to take place. So that's called the cathode. And it's given a color convention. If you look in your car, the battery in your car, it's going to have two colors in there, red and black is the other one. And that the other one goes for the anode, which is given the sign convention negative. That's the anode. And its color is black. All righty. Any comments or questions on that? Okay. So here are some of the things that you can read over and think about. Recap. And then now, for this one, we know that the electron is charged of 1.6 times 10 to the minus 19 coulombs. That was from the Mulliken oil drop experiment, you'll recall from Chem 200. The electrons spontaneously flow from the anode to the cathode. And you can tap into this to do work. E cell is a measure of the potential difference between the two half cells. So this E cell, its units is measured in volts. That's a potential difference. And the volt is defined here in this equation as the potential difference that imparts 1 joule of energy to 1 coulomb of electrons. So you can figure out how many electrons go into 1 coulomb because you know the charge of an electron. And we'll do that later. But anyway, this definition of the voltage difference can also be used to solve for energy. So energy, thus, energy equals the charge. I'll just multiply both sides by charge. These cancel, and I get a charge over here. The energy is a charge through a potential difference, much like you learned in physics, where work is a force through a distance. So we're using this charge going through a potential difference is giving rise to energy. All right. So you can think about this as, well, some people think about it as a force, but it's really not technically a force that pulls the electrons through the wire, just like gravity does. And then E cell is defined under standard conditions, which we talked about. And tabulations are made with the standard hydrogen electrode. So here we have some tabulations that I have presented here. This first one on the left is a standard reduction chart in volts. This is what you're going to most likely find online or in your textbook. So all of these half cells are measured against the standard hydrogen electrode, which is assigned 0. And then if the electrons are leaving the standard hydrogen electrode and going to the other compartment, then the voltage that voltmeter has for that setup is said to be a reduction potential for that other half cell, and it's above the standard. Now, whenever a half cell gives electrons to the standard, then it's said to have a negative reduction half cell value, and it's said to be below the standard. So we looked at zinc in our exercise, and zinc is way below the standard. That indicates that electrons are going to flow from the zinc to the standard hydrogen electrode. And the voltmeter reading that we got was 0.76 in the negative direction. If it was an analog, it would go to the left. If it was an analog voltmeter, indicating that the electrons are flowing from the zinc half cell to the standard. Note that this also implies that you can pick any two of these half cells, and you can figure out what the cell difference would be. Now, remember, we looked at the copper half cell and the zinc half cell, the one down here. And when we set that up, we knew that the electrons were flowing from the zinc half cell to the copper. And that means, when we weighed out the copper and stuff, that meant that this reaction was taking place. Copper was getting reduced to form copper metal. But on the zinc side, since it's below the copper, the opposite of reduction was happening in the zinc. So when you use this chart, you can use it as a ranking of the propensity to be reduced. Anything above anything else gets reduced, and the thing below gets oxidized. So the reaction of zinc was opposite of the reduction. Furthermore, you can find the voltmeter reading from these values. That's just the potential difference. Now that we have them all relative to the same standard, I see that the potential difference between the zinc and the copper is 1.10 volts. And that's what we found with the voltmeter in that Danielle cell. So everything you need is here in the reduction potential table. I just put the oxidation potential table and what it would look like if it existed. I mean, it could exist, but people don't use it. They use one or the other, and so they picked reductions. So this is a ranking according to reduction, whereas the oxidation potential will be a ranking according to oxidation. And you see that the half reactions involving the electrons here are all those where we have oxidation taking place. So electrons are products, whereas in the reduction table, all the electrons are reactants. Excuse me. What else? Now, the reason why you can have either one of these tables is because of that relationship there. The reduction potential of, say, some metal ion that's going to accept an electron equals minus the oxidation potential of that metal. So these are reductions on the left because the electrons are reactants, and they're going to be accepted by that thing being reduced. But I can look at these in reverse and say, oh, okay, well, in reverse, these guys could be oxidized to give up their electrons and form whatever species they form. And so that idea led rise to this ranking. Okay. But let's concentrate on the reduction table and look at the rankings, and they're all relative to each other because they're all relative to the same standard. So I can use this chart also to tell me which one is the strongest or weakest oxidizing agent or the strongest or weakest reducing agent. But when I start doing this, I have to be careful, and I have to think about what this chart is telling me and what the reactions that are taking place. So if I look at the strongest oxidizing agent, that means that thing itself is reduced. Okay, so these are all reductions. So I'm looking for something on the left side of the chart. So the strongest oxidizing agent in this chart is going to be F2. And the weakest oxidizing agent is going to be Li plus. Okay, because it has to get reduced. But if I want to look at the reducing agent, then the things that are going to lead to that are on the right side, right? Because a reducing agent gets oxidized. Okay. And so these are the things that get oxidized. So if you are given a question about reducing and oxidizing agents, you have to keep that in mind. Okay. Any questions on that? All right. Well, here's some more about some of the conclusions that we made looking at that table about the sign of the reduction potential. If it's negative, then it's below the standard hydrogen electrode, and that means it's going to send electrons to the standard hydrogen electrode, and you're going to have reduction in that standard hydrogen electrode and oxidation in the half cell that's below it. If the reduction potential in the reduction chart that we just looked at, the one on the left, is positive, that means that it's going to gain electrons. That half cell is going to gain electrons, and they're going to come from the standard hydrogen electrode. All right. Now we can calculate the voltmeter reading or the E cell reading for any half cell now that we know the rankings relative to the same standard. For example, we can find the E cell for that copper zinc setup that we used before. We can go and use just reduction potentials from the left-hand side of those rankings, right? The reduction chart, the guy here on the left. We can use just those because that's what you're going to get in your textbook and online most likely. So if I look there, I'm going to find that the reduction potential of copper 2 plus is 0.34 volts. And then I'm going to look up the reduction potential of zinc. Even though zinc is going to get oxidized, I can still use the reduction potential in this equation to calculate the voltmeter reading, or ESO. So I'm going to subtract, and then I put in the reduction potential, which is minus 0.76, and I see that I'm going to get 1.10 volts, which is what the voltmeter reading gave me. So I can use this equation. I don't have to use the equation. I can just look at the chart like we did and say, oh, well, that guy's 0.34 above the standard. That's minus 0.76 below. So the difference is 1.10. But you'll often see this equation in the textbook. And so I wanted you to know how to use it and where it came from. And you can always check it with just eyeballing the chart. Now, because of this equation here, the reduction potential of the ion is related to the oxidation potential of the metal with this negative charge. I could use this equation as well to get the same answer. So in this equation, it would be 0.34 again plus, and then I, use that on the value for the reduction. And I see that's going to be 0.76 then, and I get, again, 1.10 volts. So any of these equations will give you the voltmeter reading or the potential difference. But you don't need either one of the equations. You can just look at the chart and see how far they are from each other. All right. Any questions on that? Okay, this talks about some of the stuff we were talking about that in the chart, higher up and lower down, and what it means to be an oxidizing agent and a reducing agent. So you should read through this and understand it and go back in the chart and see if you can see what they're talking about here in this plate. I'm not going to read it to you. I don't think that would help. And then after you do that, try to do these activities on your own. Sit down and just take out some scrap paper and go through each one of these and try to do the best you can. And this is where we'll start next week on Tuesday. Any questions before we break for today? No?